Welcome back everyone to the eCoreAcademy e-learning platform. Today my name is AJay Raj, back with another geometry video for you all today, and today's lesson topic is all about dilations in geometry. But before we get into the meat of today's lesson and what we're exactly going to be doing and executing today, I just want to ask you guys to please make sure to subscribe down below, smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our channel's latest posts at eCoreAcademy. It's all very much greatly appreciated. So like I was saying, today's lesson topic is all about dilations. If you haven't watched my previous video set called Transformations, I made a part 1 and part 2. It's a very in-depth group of chronological order videos that goes in depth about transformations in geometry, as dilations are a very specific type of transformation in geometry. So I'd first recommend that you go and view those 2 videos before viewing this one, or at least viewing the transformations part 1, so that you get a little bit of a hint of what dilations are and how exactly we're going to be carrying out this process. There's going to be multiple terms that I have referred to in the original transformations part 1 video that I go in depth with the definition and details of them in concepts that are related in geometry. So if you are a bit confused, I will try my best to try and go over that, but then again, we're trying to move here at a quick and easy pace so that we can cover everything in the least possible amount of time so that you all absorb this information properly. So without further ado, let's get into dilation. So today's lesson's topic or theme is all about discovering what is the dilation process and how does it prove similarity. So in my previous transformations video, I had mentioned 3 other transformation processes, and I had explained them, but those are translations, rotations, and reflections. But those are actually quite a bit different from dilations, even though I did mention them all together group-wise as transformations. Dilations are its own specific type of transformation that does not relate exactly or correlate exactly with those other transformations mentioned before. So let's get right into today's lesson. So first we have our similarity section. So remember how we said one of our goals of today's lesson is to discover how dilations can actually represent similarity through its processes. So if you don't already know what similarity is, or similar figures, what they are figures which have the same angle measures as well as proportional corresponding side lengths. So similar figures, even if it's represented on a blank transformation plane or even on a coordinate plane, are actually figures that have the same exact shape but do not have the same size. So as you can see here, my title here, it's how to represent similarity with dilations. So with this given information and with the explained process that a dilation encounters, and of course the definition of a dilation, we can actually prove through geometric proof that dilations actually maintain similarity and they represent similar figures. Corresponding the pre-image to the image. So similar figures are figures that have the same angle measures and proportional side lengths, meaning that if you were to divide corresponding side lengths by each other, they would have the same ratio. That means they're just both proportional. These 2 shapes are proportional. They have the same shape. It's just that the only thing that they don't have is the same size. So with having the same shape, they would have the same exact angle measures in their intersection. So say, for example, a triangle, they would have the same 3 angle measures, and they would have proportional side lengths, meaning all of the side lengths divided correspondingly to their pre-image and image will have the same exact proportion ratio. So dilations prove to develop similarity between a pre-image and image through its process. Now, if you can recall, pre-image is what's originally given, is a figure that's given, and the image is what's the output, the product that's given and preceded after a transformation is conducted. So dilations help prove the similarity process, and I will draw this little example here. So if you're given a triangle like this, if you're given a triangle, we'll label it triangle A, and we're given another triangle, triangle B. Well, the properties that these 2 triangles have to be in order to represent similarity, and if you don't already know, this is the sign for similarity. It's a little wave or curve that just shows that angle A is similar to angle B. In order to prove that angle A is similar to angle B, you can use similarity properties, which would be to see if they have angle measures, so equal angle measures. if they have proportional side lengths as well. So those are the two main qualifications if you're just trying to prove similarity. However, in order to shorten both of those terms, you can just prove if one is a dilation of another. So you can use the dilation process to also prove it. So that's what the main goal of today is, to separate these two concepts and try and just use the dilation process to prove two similar figures, to prove similar figures as similar to each other with a reasonable proof that isn't as complex as proving angle measures and proportional relationships. Let's move on. So similarity part 2, this is all about congruence transformations. So like I mentioned in my first video, this should be a very relative term, a common term. It's rigid motion. So I'll just highlight that real quick. Rigid motions. That's very important. You should probably keep that down. And that's probably one of the main items that students get confused with and they find actually quite tricky. So and it's not. So rigid motions are transformations, as you already know what a transformation is. It's a one-to-one mapping of a figure, and rigid motion is a transformation or transformations of which preserve the shape and size of a figure. So that means after you alter or move the location of some sort of figure, it's still going to be congruent to its pre-image. So that means if you're going to be moving this figure here, say for example, you're going to be moving figure A, triangle A here, you're going to try some kind of transformation. Say, for example, we're doing a translation, which is a sliding of this figure, and we're sliding it over to triangle B. That means that triangle B must be exactly congruent. It must be the exact same shape and size, but just not the same location. So, like I said, I use translation as an example, but the three types of rigid motion transformations are translations, reflections, and rotations that maintain congruence, and that's the main differential between translations, reflections, and rotations versus dilations. That's why I separated these two lessons, because they're two different kinds of transformations. And dilations have a different type of relationship transformation from its pre-image to its image, and we'll get into that right now. So dilations part 1, all about dilations. So a dilation is a transformation, by geometric definition, is a transformation that changes the size, but not the shape of the figure. So unlike a rigid motion keeps the same shape and size, but the dilation changes the size, but still keeps the same shape. And what that basically falls under is the law of similarity. So as it falls under the law of similarity, we can assume that, let me just write this down real quick. So if it falls under the law of similarity, a dilation process, that means that dilations maintain similarity. Sorry if that got cut off. I'll just erase this real quick so that you guys can get that down. So since it follows the law of similarity, that means that it will result in the fact that dilations maintain similarity through a figure altering by only affecting the side length. So what that's saying is, since a dilation is affected by the law of similarity, meaning it changes some figure by altering its size and location, not its size and location through its process, but it still maintains similarity. And what that means in specified terms is that dilation will maintain a figure's angle relationship, meaning all angles in the figure will still be the same, which keeps a figure similar. So I'm going to write that here. Angles show similarity. That's what I'm going to write here. Angles show similarity. And one other thing that dilations do is they only change the side length, but they change the side length by an equal increment in order to keep the side lengths proportional. So I'll just say that here. We'll say equal increment increase. Equal increment increase. And that's referring to side length. Write that here. So basically what I'm saying is, if you have a dilation and you're trying to double the side of if you're trying to double one side of a figure, well, what you'd have to do is you'd have to double all other sides of that same figure in order to maintain similarity between the pre-image and the image, so the original to the altered copy of it. So let's look at the dilation process now that we have a good grasp of what actually dilations are and how they're representative of similarity. Let's look at their process. So in order to conduct a dilation on the coordinate plane, you would need to know what the dilation scale factor of the figure would be, as well as the center of dilation. So basically what that means is, if you're given a blank transformation, all the information that you would need to know is the scale factor and the center of dilation, and I will explain that right here. So you have to write that down here. I'll write it out. Scale factor and your center of dilation. So just how, just like reflections, rotations, and translations, the other three transformations that I had mentioned before, and the other three main transformations in geometry, they have unique processes, unique components to their processes that would, include, for say, for example, rotation, you'd need the angle of rotation and the center of rotation. For a reflection, you'd need the line of symmetry or the axis of symmetry. And for translations, you would need your translation vector or your distance of slide. And for a dilation, of course, you would need your scale factor and your center of dilation. So let's get into what exactly these components are. So the scale factor, like I mentioned, is the ratio of the side length of the image to the corresponding side length to the pre-image. So that means, like I said, in any transformation, you're going to have, your original, I'll use a square this time. So if you have a square here, so we have a square here, and you're trying to, let's say this is a parallelogram A, because it didn't come out exactly straight, but we'll say this is a parallelogram A, and we're trying to dilate this figure, correct? In order to dilate the figure, you would need a scale factor. So what that would do is, you're taking a side length, and you're basically multiplying that side length by a certain amount. So you're basically multiplying that side length by a certain amount in order to get a corresponding side length to the pre-image. So say, for example, you wanted to double the side length here. So what would happen is, your image would have a side length that's double that. And basically what's factoring out the value that's being used to describe the process in which one side length is being doubled to another side length, in which term an entire figure is being doubled in order to represent another figure, is actually the process of a scale factor. So instead of saying doubled, your scale factor would be 2. So I'll just draw this parallelogram out. Let's assume that this is a square, actually, so that makes a bit more sense. So let me draw a little square here that looks similar to what I drew in my second figure. So if you're doing a dilation and you're trying to double the side length, which in turn doubles all the side lengths of each side length of similar figures, what happens is, the way that you would represent that is, instead of saying this side length is doubled, or this figure has doubled the side lengths, or doubled the length of sides from its pre-image to its image, what you would say is it has a scale factor of 2. So scale factor equals 2. And I'll go into depth on exactly what that means. And next we have our final part of dilations and their processes, and we have the center of dilation here. And it's the point of intersection of the lines that connect each point on the pre-image with its corresponding point on the image. So if we're given a diagram right here, it's very self-explanatory with the diagram in place. So if you're given a triangle BAC, say for example this triangle BAC is the original pre-image, and you're trying to dilate it to triangle EDF or DEF, depending on how you would like to pronounce that. What would happen is, you would have to be identifying some sort of center of dilation. And what happens is, in order to calculate your center of dilation, or in order to calculate the dilation that you'd be given, you're given a scale factor, correct? And what you're trying to do is, you're trying to represent that scale factor and create an image. So the process works like this. You're given your original figure, and you're going to calculate the distance that each point is from the center of dilation. So that means that, say for example, this side is 6, let's say that this side is 6 units away, and this side is, say for example, 4 units away. What happens is, as you're given that information, and you're given that, say for example, your scale factor is 2. So if your factor equals 2, what you would do is, you would count double the amount of distance that these original points are to get your image. So you'd count the distance that it is from the center of dilation. Say, for example, as we see here, it's 6. So we're just going to double that to get 12, and we're going to count 12 units out to get one of our points of our triangle. And all you need to determine a figure's overall shape is just to merely determine what its points are and where it is in general, because then you can just connect your lines there, which develop your angles in turn. And as you can see here, these little arcs right here, I'm going to circle them. This arc here, and this arc here, it corresponds to its corresponding arc here, because that's just showing that these angles are all congruent to each other, meaning that they are similar figures. So dilations part 4, we're going to look at blank transformations. And if you don't already know what a blank transformation is, it's basically a transformation without any calculation and through pure estimation on a plane, on basically a blank plane, and it just shows the overall visual of a dilation. It's just basically showing an estimated version of what a dilation would look like. So all you would need in order to conduct a blank transformation on a graph is the center of dilation represented by a point and whether or not the transformation is an expansion or contraction. So like I said, you need the center of dilation and the scale factor, but the scale factor has two different types and two different characteristics. That means the scale factor can either be a contraction or an expansion. So that relates to the scale factor. Oops, forgot the R. So what an expansion is, it's one type of scale factor, and the expansion is when the absolute value of the scale factor is greater than 1. And of course, your contraction is the complete opposite. It's when the absolute value of the scale factor is less than 1. So before I get into the actual numeric values and algebraic representation of expansions and contractions, if you look at these vocab words originally as they appear to you right now, you might be thinking, well, I've actually heard of those before. Because when you think of expansion, you're thinking of expand. And what expand means is, the root means increase. So that means a figure will increase under a dilation. And a contraction is going to be a decrease or a shrinkage through its scale factor. And in order for a figure to have a scale factor that'll cause an expansion, its absolute value, meaning the absolute value of x being the scale factor, would have to be greater. Sorry, that should be greater than. Let me fix that right now. Would have to be greater than 1. But in order for it to be, so I'll just link that here, and in order for it to be a contraction, you'd have to have the absolute value of x being the scale factor that you're given, meaning it has to be less than 1. So the absolute value of x must be less than 1. And just to say that in layman's terms, in order for an expansion to be a scale factor to be an expansion, it just has to be a number that's greater than 1, meaning it can be a negative number, but the digit itself just has to be greater than 1. And if that number is not a decimal and it's not 0, then it's an expansion. But if it's a decimal, then it has to be a contraction. So no matter if it's negative or positive, it's going to be either expansion or contraction. And yes, I want to clear that up. You can have a negative scale factor, but I will get into that in our later lesson, which is going to be all about extended problems for dilation. So just stay in tune for that. It'll be coming up very soon after this. So let's look at dilations part 5, and this is special scenarios. So when looking at a positive scale factor for a dilation, you would always end up with an image on the same side of the center of dilation as the pre-image. So what I'm saying is, if you have a scale factor that is a positive number, and you're given a center of dilation, or like this, your figure, and let's say this point represents an original pre-image. The figure under a dilation will always be on the same side of this point, meaning it'll be on this side over here. However, when looking at a negative scale factor, the side lengths of the figures will have the same proportion and same exact properties as a positive scale factor, but its location of the figure will be on the opposite side of the center of dilation. So this is your center of dilation, and this is your figure here. Your new dilated figure with a negative scale factor would actually be here, going in the opposite direction. It'll be located on the opposite side. And when the scale factor is 0, the transformation of the figure does not exist. So, that means if you're multiplying a value with the scale factor of 0, it will not exist. All right, let's move on. So dilation is part 5. So this is just a recap of what I was saying: special scenarios, negative scale factors, and when the scale factor is 0. Now let's look at circles. This is our final special scenario here, and I just added this here if you guys want to take these notes down, but you can always pause there if you want to take the notes there. I just wanted to add that again about negative scale factors and when a scale factor is 0. All right. So let's look at dilations part 6. So this is all about circles, and this is our final special scenario here. So one figure other than a polygon that can undergo a dilation through a scale factor is a circle. So you might be thinking all these transformations like, oh my god, you have to have a polygon. How is it possible that you can have a curved figure? Well, a circle can actually undergo a dilation. And a polygon is merely a figure with straight sides. It has straight sides. And a circle like this is something that does not have straight sides, and it has all curves. And the radius of a circle is what is affected in this process and is used for proportionality. So like I said, the side lengths of a dilated figure are actually what are affected. But if you look at a circle, there's no straight edges that you can merely think of on the figure itself. However, a circle will always have a radius. So that's the distance from the center of a circle all the way to all points of its outer edge. It's always equidistant to all points of the circle. So you can use this radius, and you can use calculations to discover what the you can discover what exactly the dilation will be, how it will undergo, and what the scale factor will be. So basically, you're just going to do the same thing as you would to a side length. You'll multiply it by the scale factor. So you're just going to multiply radius by a scale factor. And one thing that I just want to put out there is, I was really off. So one thing that I just want to really put out there is that a really interesting statement that I just figured out was that all circles are actually going to be similar, and that can be proved directly through dilations with the radius relationships to preimages and images when they're interfaced with each other. So I'm just going to write that out here. All circles are similar under the laws of dilations. So I just want you guys to, get acquainted with that, but I will explain that in later videos and when we go about circles and conic sections, which is farther down the line, but I just wanted to get that out there because it did relate to our topic all about dilations. So let's move on to our practice problems. I have 4 practice problems here left in the video. I just want to go through the different examples that I had come across, and I want to show you what their application is in actual problems in geometry. So first type of problem is deriving the scale factor. So what is the scale factor mapping the first triangle to the second triangle? All mapping means is what basically dilates this first triangle to the second triangle. So we're going to look at these side lengths, and we can see that this side here that I'm marking off is going to be corresponding to this side here because it's the longest side, or the second longest side, and this bottom side here is going to be corresponding to this bottom side here. So since we've figured out what the corresponding sides of these triangles are, we can immediately go and calculate what the dilation process and the scale factor is. So what we're going to do is we're going to take this, since we do not know this side here, it's side length here. Sorry about that. Let me just go back real quick. So if we do not know this side length here, that means we cannot calculate this side length here under a dilation. So that means we lose this side length here. So we cannot calculate the side length here. And since these two side lengths are also similar, these hypotenuse of this triangle, we cannot either calculate these side lengths together as well. So since we're only given these side lengths of 2 sides, we're going to be calculating the scale factor. And in this process with dilations, you're actually not going to take into consideration what your unit of measure is. So we can take apart this inches sign and this centimeter sign because they're actually irrelevant in blank transformations. And that's what I wanted to get across by putting those different measurements out there. It's just that centimeters and inches, different units, they actually don't affect blank transformations, and they don't affect their process. So what we're going to do is we're going to divide this side length here by this side length here because we're trying to figure out what the scale factor is. creating this this figure to this figure, mapping this figure to this figure. So if we divide 8 by 2, we get that the scale factor is 4. And since the scale factor is 4, it's going to be a dilation that dilates this first figure here by 4 to get this next figure here. And since this triangle is not considered a right triangle, that means that this line here does not necessarily have to be greater than 16 and 8 inches. So since it's not specified, we can just merely assume that this side is equivalent to this side. This side being 16 inches and this side also being 16 inches due to our dilation and scale factor. But if it were specified to be a right triangle, that means that those side lengths would not be accurate, and that means that these two figures would not be similar and could not calculate a scale factor out of. All right, guys, let's move on to the next lesson. Next problem. So this is also deriving the scale factor, but a little bit of a different concept, a little bit of a twist. And we're going to calculate what is the scale factor from the first figure to the second figure. So we're going to look at this circle. So this is all about circles here. I just want to asterisk this. So you don't necessarily need to know this, but since this is an enrichment program, we're trying to incorporate some of these higher level concepts in geometry and math. So if we see here that this circle here, this original circle, I'm going to label it circle A, has a radius of 3. So I'm going to write this here, r equals 3. And we see that our second circle here has a radius of, circle B has a radius of 8. What we're going to do is we're just going to merely divide this, this figure here has a diameter of 8. And we're merely going to divide this original radius of circle A and divide it over the radius of circle B. So if you're looking at circle A and we see that it has a radius of 3, we need to calculate what the radius of circle B is. So since we're given the diameter is 8, which is the length across the entire circle, we're trying to find the radius, which is half of that. So we're going to divide 8 by 2, and we're going to get that the radius equals 4. So since we're given this relationship of radius 3 here and radius 4 here, we're merely just going to divide A over B, which equals 3 over 4. So that's our scale factor for this problem. Now we're going to start graphing blank dilation. So let's graph the dilation. Let's graph the dilation of this figure under a dilation of 2. So I'm going to draw this out for you because blank dilations, it's all about drawing it on blank plane. So I'm going to draw this on my chalkboard here. So I'm going to draw out a square. And what we're going to do is we're going to try and show this dilation of this figure under a dilation of 2. And let's say that the center of dilation is right here. So what we're going to do is we're going to look at these points. And basically what we're going to see is we're going to try and double this distance from these points. And what happens is that we know the figure is going to be somewhere here. So we're going to estimate it, eyeball it, and we're going to try and create a figure that is twice as large. So as you can see, this figure is estimatingly, since a blank transformation plane does not have any specified units, we're just going to estimate this to say that this is a dilation of this original figure A, as it's given to A prime, which is its dilation of a scale factor, under a dilation of a scale factor of 2. So as you can see here, this distance will be 1/2 of this distance right here. Same thing with all of these other points and the relationships. Finally, for a final problem, it's going to be graphing a blank dilation continued. So this is another example, and I'm going to be incorporating a negative scale factor, because remember I introduced negative scale factors and how I said they're a bit different from positive scale factors with similar properties but different location requirements. So let's draw this triangle out here. Triangle A, we'll name it triangle A. And we're trying to put it under a dilation of negative 0.5. So since we see here that we have a 0.5 dilation, that means it's going to be a contraction. That means the figure is going to shrink, and it's going to shrink by 1/2. And since we know that, and also we're going to include this little center of dilation, that's our center. And since we know that it's a negative dilation and it's going to be a contraction, we're going to make this triangle approximately 1/2 of its original size. 1/2 of all of its side lengths is going to be shrunk by 1/2, and we're also going to be placing it on the opposite side. Because remember how I said the making it a negative dilation means we're going to place it on the opposite side of the center. And what also happens is, with this new dilated triangle, what also happens is its distance from with all of its points from the center of dilation is going to be 1/2 of this distance. So I'm going to say 1/2 here of this distance. All right, guys. So that's it for today's lesson. I know it was a bit of a little bit more difficult of a lesson, a lot to obtain, and a lot of concept difficulty, but I will be going over this in depth with my next video, try and get you more acquainted with problems, because it's not necessarily about retaining lessons, but it's also about just doing them, because doing them actually helps you understand them probably the best of all. So that's what math is really revolved around, and that's what geometry is really revolved around as well. So thank you guys once again. It's been eCoreAcademy e-learning platform. Please make sure to like and subscribe down below. Hit that post notification bell to our channel at eCoreAcademy. Visit our website at eCoreAcademy.org to get full unlocked access to all of our videos with included worksheets, note sheets, and integrated quizzes that go along with each video, as it's much more of a bonus. So please make an effort to make an account there and get all of that full unlocked bonus access. And finally, you can email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out to us. And similarly, you can look at all of our socials at Facebook, Twitter, and Instagram if you want to share all of our videos and look at and see what content we have out there. Once again, guys, I had a pleasure making this video. I hope you guys enjoyed. And this has been AJay Raj, and I will see you guys in the next one. Peace out.